So the principles behind electrochemical reactions involve the transfer of electrons from one species to another. It's the basics here. We've talked redox reactions before, reduction oxidation, remember? We've talked about how to label something as a reduced or an oxidized reactant. We're going to talk a little bit further about how to actually separate redox reactions into a reduction reaction and an oxidation reaction, and how to balance these reactions. And then we're going to follow that up, this particular first part of lecture, by understanding what a voltaic cell is. Voltaic cells being essentially batteries, okay? Things that conduct electrons across a membrane from one part to another. Okay, so movement of electrons is primarily what we deal with in this chapter. Yeah. All right, so that being said, we have to go through and we have to remember how to assign oxidation numbers. This is something you did in Honors Chem. This is something we did over the summer as part of our summer homework so that we knew what our oxidation numbers were and so on and so forth. The principles are still the same, okay? And there are certain rules, so we're going to go through the rules of oxidation numbers again to make sure that we remember. One of the ones you probably remember and will never forget involves oxygen. What is the charge of oxygen always? -2.
I was going to say.
Oxygen's always going to be a -2 unless it is in the peroxide ion, in which case it's a -1. That is a rare occurrence. Okay? So, when we talk about oxidation and reduction reactions, we have to recall that mnemonic that we talked about, oil rig. Oxidation is going to be a loss of electrons, so oxidation is loss is oil. That means that a species that moves from the reactants to the products loses electrons and becomes more positive by doing so.
We did this earlier this year.
Oh, you've done this before. You've definitely done this last year too.
You don't remember oil rig?
We talked about oxidation numbers in Honors Chem
Oh, I
too.
always loved it.
Polyatomic ions, we do charts, all kinds of lovely stuff. Yep. So that being said, in this particular example reaction, on the reactant side, zinc in its elemental form, remember anything in its elemental form, aka solid or gas, etc., is going to be a oxidation state of 0. On the right side, it becomes a +2 charge, so it has lost electrons to become more positive. So just review of oxidation. Reduction is the opposite. The thing gains electrons and becomes more negatively charged. So in our example up here, we have hydrogen on the left as a +1 charge. Hydrogen on the right is in its elemental form and has now got a charge of 0. Hopefully some of this is coming back to you. A little bit of review of oxidation and reduction in basic form. All right, so our next step is then to be able to identify what is oxidized and what is reduced. We have to use oxidation states on both sides to do so. Now, one of the things I do want to make sure we remember, most commonly, what type of element loses or gains electrons? Metals or nonmetals? Metals. Metals are the ones that can gain or lose electrons, okay? Just a general rule of thumb. Can a nonmetal gain or lose electrons? Absolutely. But most commonly, we are going to look at the things that are metals and nonmetals. And remember that hydrogen can behave as both. Okay, so hydrogen may be the thing that gains or loses electrons, as we see in this example. Okay, the thing that is reduced is then inversely referred to as the oxidizing agent. And the thing that is oxidized can also be referred to as the reducing agent. Most of the time, we look for the reactant that is oxidized or reduced. And very rarely will I ask you, what is the oxidizing agent? What is the thing that is the reducing agent? Because it just kind of confuses the situation, right? They're inverse of each other. For our purposes, we want to be able to identify the thing that is oxidized and the thing that is reduced. Oxidizing agent and reducing agent are just kind of extras. Fine. All All right, so let's go through the rules for assigning oxidation numbers. First thing is going to be elements that are in their elemental form, so that solid form, have an oxidation state of 0. If it's by itself, not attached to anything, has no charge, then it has an oxidation number of 0. The oxidation state of something that is an ion is the same as its charge. So think if calcium is in the 2+ state, then it is a 2+ charge. If it's by itself and you're told that already. Make sense? This is like the obvious part of oxidation numbers and their rules. Our next step is to talk about oxygen. Nonmetals are going to tend to have negative oxidation numbers, and oxygen is usually a -2, except for that one peroxide ion, where it can have a charge of -1. Hydrogen is only going to be negative or +1. Depends on what it's bonded to. If hydrogen is bonded to a metal, then it acts as the nonmetal and has a negative charge. If hydrogen is bonded to a nonmetal, then it is going to act as the positive metal. That one's kind of complicated. Please make sure you understand how hydrogen is going to behave. Most nonmetals will have negative charges for their oxidation states, with the exception of hydrogen. Remember, hydrogen is the weird one. It can act as a metal or a nonmetal. -1 or +1, depending on what it's bonded to. So when hydrogen is bonded to oxygen, is it going to be positive or negative? What do you think?
Positive.
Positive, because oxygen is the nonmetal, hydrogen would have to be the metal at that point. When hydrogen is bonded to lithium, Li, is hydrogen going to be positive or negative?
Negative.
Negative, because it is bonded to a positive metal. Another rule of thumb, fluorine, always a -1. Remember, fluorine is the most electronegative on the periodic table. It gets the privilege of always having a -1 charge. The other halogens that are not fluorine are either going to have a -1 charge or they're going to be positive. Depends on what they're bonded to. When they are in polyatomic form, the halogens tend to have positive values. So think something like ClO4 -1. You remember your polyatomic ions? That one's perchlorate. In this case, what is the charge of an oxygen? Always a -2. There are 4 of them, which means the total charge of oxygen has to be a -8. The overall charge on the molecule is a -1, so what does chlorine have to be?
7.
+7. Okay, so when they are in polyatomic form, the halogens can be something other than -1, with the exception of fluorine, which is always a -1. All right. In a neutral species, the sum of the oxidation numbers should be 0. In other words, for a species like this, the sum of the 2 oxidation numbers should be 0. Okay? Fluorine's going to be a -1 in this case. Sodium is going to be a +1 in this case. You add them together, they're 0. If you have an ion of some kind, the sum of the oxidation numbers must be whatever the ion's charge is. So in the case of our ClO4-, you would add the 2 oxidation numbers together to get the -1. Just reminders of those things. I've seen this before. Who recalls it? Kind of a vague recollection of doing this, yeah? We did it in a more complicated way where we made charts and all of that lovely stuff. If you remember how to do those and you liked them, you're welcome to continue doing them. But basically what we did is we made... And it was like number of atoms, the charge, and you brought it down.
What? I'm copying down the PowerPoint.
right? Remember doing this a little bit? This is how we did it in the past. Same ideas here, except that I'm not going to require you to do these charts. This is something we did in honors chem. I didn't require you if you figured it out. Some people can do this math really quickly and kind of see the patterns. Some people can't. Do whatever makes it work for you. I care that you can find oxidation numbers and that you can use those oxidation states to determine what gets reduced and what gets oxidized. I don't care how you get to this thing is reduced and this thing is oxidized as long as you're doing it right. Okay, next thing we're going to learn is new, and it's the balancing oxidation reduction equations using the half reaction method. You cannot just balance these things visually. This is not a put a 2 in front of something, put a 3 in front of something else, and balance the overall reaction. It doesn't work that way. A lot of times it's because when we're doing these reactions, we're doing it in either an acidic solution or a basic solution. The first of the two ways we're going to learn is using an acidic solution. Okay? The first step in balancing any of the oxidation reduction reactions we see is going to be to figure out how to split them into two reactions. We need the oxidation reaction, we need the reduction reaction. From there, then we're going to balance each one. We're going to talk about how. Okay? This method is going to involve adding things that make up water. So we can add water molecules, H2O. We can add hydrogen atoms, H+, because we're in acidic solution. Or when we balance this in basic solution, we can add OH- molecules to balance it. So just kind of remembering some of your principles of acid-base chemistry. H+ is present in acidic solution. OH- is present in basic solution. And if you have both H and OH on one side of a reaction, what do they make? H plus OH makes H2O. Okay? So those are the principles that we're going to use to balance these half reaction methods. You have to know if it is in an acidic solution or a basic solution in order to do this. So you will always be told, balance this reduction reaction in acidic solution, or balance this reduction reaction in basic solution. And you'll see why here in a second. But we are going to use the half reaction method, and the first step is to split them up. So how do we identify what is reduced and what is oxidized? Oxidation numbers. We need to figure out what our oxidation numbers are so that we know what's being reduced and what's being oxidized. One of the things to remember is that if it's being reduced on the left, so let's say we're talking about the zinc 2+ situation from our previous example, that zinc should stay together, right? Zinc will make zinc. You can't get rid of that atom, okay? That's one of the major hints for our half reaction methods, but there are steps involved. You're going to want to use them. First one's going to be to assign the oxidation numbers to determine what gets oxidized, what gets reduced. Very first step in this particular reaction type. What? I don't know what that means. First step, get your oxidation numbers so you can determine what's oxidized, what is reduced. Second step, separate them into two reactions. And we are going to go through this together a couple of times. We're going to do some examples. You're going to do them on your own. That's what the next couple of days in class is. Today and tomorrow. Technically. Possibly Monday if it takes so long, but I do it. So you're so disappointed. You're fine. So here are our first two steps. Get them written down for me. I will ask you to write these down for your daily Q tomorrow, just so you're aware. I'll ask you what are the steps for balancing half reactions in acidic solution. And one of the things you can do is take a picture of your notes. So if you have them in your notes, you can just take a picture. No, you gotta write them down. Nope, this is just the first two. These are the first two steps, but it's like, what are the steps? These are the first two steps.
That's real easy.
Yeah, no, we're not done. They're not balanced yet, guys.
That doesn't seem right, but okay.
Nope.
Okay.
Next thing to do is to balance each half reaction individually. And in order to balance these reactions, it is not just a matter of number. What we're going to be doing is we're going to balance any elements that are not hydrogen and oxygen first. Okay, and you may not even have hydrogen or oxygen present at the beginning. That's okay. There are only two things 3 technically, that you can add to a solution that is being balanced in acidic solution. Those 2 things that you can add are H plus ions and electrons that are negatively charged. Because one of the things we have to balance is the atoms themselves, and then at the end we have to balance the charges. Because if it's got a charge on one side, it's got to have that exact same charge on the other side. Everything has to balance, not just the elements themselves. So the first step in balancing each half reaction is to balance the elements that are not hydrogen or oxygen. Anything not hydrogen or oxygen. So say zinc, right? If you have 1 atom on one side and 2 on the other, put a 2 in front of the one you had on the one side. Next thing is to actually balance O by adding water. So if oxygen is present on one side of your reaction but not on the other, add the number of waters you need to balance just the oxygens. Next up is going to be to balance those hydrogens you just added because of water by adding H plus to whichever side needs the H's. As many as you need. Don't worry about charges at this point. The very last step of this particular method, for each half reaction before you add them all together, the very last step is going to be to add electrons to whichever side needs to be balanced as far as charge is concerned. Now don't forget, H's are positively charged, electrons are negatively charged. So you're trying to balance positive and negative so that each side has the same charge. If that means you have to add electrons so that the charge on the left side is 2 and the charge on the right side was 8, you had to add 6 electrons to get that charge down to 2 so that both sides match. You can only add electrons at this point. You shouldn't be adding H's anymore. You add H's, you've unbalanced your hydrogens again. Once you have balanced both half reactions, we move on to step 4. Put them back together. We can't put them back together unless they have the same numbers of electrons in each. So what we're going to do is we're going to multiply to get the numbers of electrons that are present on whatever side they might be present on in your half reactions to get those numbers to be equal. So if one reaction has 10 electrons and the other only has 2, you have to multiply that one reaction by 5 to get it to have 10 electrons as well. Number 4 is going to save you a lot of a headache before you do number 5. Number 5, once you add the half reactions, if you followed everything up to this point, the electrons should cancel each other out. There should be no free electrons in your final balanced equation. Can there be hydrogen positive atoms? Absolutely. Can you have acidic protons present? Yes. Okay. But at this point for step 5, you're adding both things together. You're crossing off what's present on both sides of the reaction to reduce it like we've done in the past. And then you are just going to make sure, you're going to double check your work for the last ones. One says make sure it's balanced according to the elements. That's what mass means, right? So make sure that the number of hydrogens on the left is the same as the number of the hydrogens on the right. The last thing is to make sure that your charges are balanced so that the positive or whatever your charge is on both sides should be the same at this point if you did everything up till now. But in this class and in future classes, you always are going to have to go back to, did I check my work? Does it make sense? If something isn't balanced, you did something wrong. And that is balancing half reactions in acidic solution only. Basic solutions have an additional step, and we'll talk about that here in a second. We're going to go through a practice problem in lecture, then we're going to go through one together, then you're going to do them on your own. So it's not as bad as it seems. It's just a different method for balancing. It's really not. It's actually really fun when you get used to it. I like it. I love balancing electrochem reactions. But electrochem was one of my 2 specialties when I was in grad school.
Okay, then there you go. That makes a lot of sense.
Reaction is my specialty.
No, electrochemistry.
Certified in oxidation.
Electrochemistry and analytical chemistry, 2 of the best topics you can possibly study. No. All right, here we go. Here is our practice problem. Have your steps out.
They're right here and highlighted.
Good. All right.
I didn't make it that far apart.
Here we go. This is our reaction. Get it written down. Use a new sheet of paper. Okay? You can continue writing it, but if you're like halfway through a page, you're going to run out of space.
Like, this is not enough space.
Yeah.
See, that's my problem.
Just trust me.
No, it's not.
That's my problem. Put it in between stuff.
It's not my fault. You did that. You did that to you. I don't want to tell you. All right, here we go. Write the reaction down. That's the first step. Come on. Very, very whiny today. Very whiny today. You're telling me.
I didn't realize.
All right, get it written down. Looking back at your oxidation steps, the first step is to do what once you have it written down? Get oxidation numbers. So start trying to do those oxidation numbers on your own. Remember, you're looking at the metals to change, not the oxygens. Oxygen will not change charge from left to right, so don't try to make that happen. Look at anything that isn't oxygen first. Yes, ma'am. So you already know that oxygen is always a -2, right? Yeah. And you know this whole thing has to be a -1. So if this is -2 and there's 4 of them, and the whole thing has to equal -1, what does MN times 2?
I feel like we should be using pencil.
Okay, plus 10.
7. At least I'm not writing first.
Yeah. Yeah, 7 plus, right? So write 7 plus underneath it.
Handwriting kind of looks like it.
Next up is your carbon over here. So you got 7 plus -2, right?
It's
Always
not a
-2.
plate.
So you can put oxygen as -2 all the way across. You already know that manganese is 7 plus on this side and 2 plus on this side. We've already told you that, right? What is carbon going to be on this side? That's the next thing you need to figure out. Does that make sense? That's what you're doing.
Literally get out.
All right, get your oxidation numbers assigned, please. Do some practice. You good?
Right? Yeah, I'm still just a little bit behind. I'm on step 2. Like writing step 2 down.
Oh gosh.
Dude, did I not bring it? Oh.
I went to the potty.
That's what he gets for doing that. What's up?
If it doesn't, so the CO2 doesn't have a charge on it.
Correct. So they have to add together to be 0. Does that make sense? So carbon on this side is going to be what then? 4. What was it over here?
6.
6? 8. 6. Divided by 2 is positive 3. Right? Because there's 2 carbons. Here's what your oxidation states should be. You'll notice that we did not look at oxygens because oxygen is like our benchmark. It's always a -2. It's how we determine everything else around it. Yes, ma'am?
So like those are just like the
So this one is, yeah, so it's manganese, then carbon on the left, then it's manganese on the right, carbon on the right. Okay, and so this one follows rule 2, right? It says that if it gives you a charge, that's what the charge is. Next thing to do is to figure out reduction, oxidation. Since manganese goes from a very positive number to a less positive number, it is the thing that gained electrons and was reduced. Since carbon went from a +3 to a +4, it lost an electron and was oxidized. Okay, so remember oil rig. Next thing to do is to write the 2 half reactions by themselves. So how are we going to do that? Well, we know that manganese was reduced, right? So we know that's one of the half reactions. What should be on the other side of the reaction? And then? Anything else? No, not for now. What's the other one going to be?
C2O4.
There's our 2 half reactions. So that is step 2 for the balancing the half reactions, is to get them into half reactions. Yes, ma'am?
Oh, I see. Where did you get
For manganese?
Yes.
So if MnO4, it's okay. If MnO4 has a -1 charge, then you know that whatever Mn is plus 4 oxygens is going to equal -1, right?
Yes.
Okay, what's oxygen? Some number plus -8 equals -1. Does that help?
Yeah. Okay.
Okay.
Now I know what
All right, what's next? On your steps.
3A.
To actually start with 3A, the first thing says, balance the numbers of things that are not hydrogen and oxygen first. So how are we going to do that up here? First things first, do we have to do anything to this one?
Yes.
I've got
Yeah.
1 manganese and I've got 1 manganese. Do I have to do anything to change that? No. What about over here? I've got a 2 here. I need 2 carbons. What's next?
Move electron.
3B.
Which is
balance O by adding H2O.
balance our oxygens by adding H2O to whichever side we need. Oh, ignore that. We're not going to do their method. All right. How do we balance our oxygens here? Do we need to do anything? Do I have equal numbers of oxygens on both sides?
Yeah.
Oh, good.
Technically.
What about over here?
No, you
You're gonna
don't.
need to add it.
You're gonna need to eat.
I've got 4
over
oxygens
there.
on this side, right?
Yeah.
So in order to get 4 oxygens on the right
You
side,
need 2 H2Os.
I'm going to add
Wait.
4 H2O.
Oh, I was thinking the H2. Oh, that's. I thought the 2 was assigned to the O for a second. Yeah. I was
Now we
wrong.
don't have any hydrogens.
Now we don't have hydrogens on the left side, even though we have them on the right side. So what do we have to do?
Yeah.
Add our hydrogens to the other side in the form of
H plus.
H plus. How many H's do I have on the right now?
8.
4 times 2 is 8. So I'm going to add 8H plus to the left side of my reaction. What do I have to do next here?
Balance the charge by adding electrons.
All right, so on the left side, what's my total charge? Think
0.
before you act. Your total charge when you add 8 plus 1 minus is 0.
7.
That would be 7 plus total on this side.
Oh. Okay.
What's the total charge on this side?
2 plus.
2 plus.
Back to sixth grade.
Remember we said we could add electrons, but we cannot add anything that's positively charged. So how many electrons do we need to add to the left side to get the charges to match? I need to add 5 electrons on the left.
Okay, how does that work? Like, how do you just add electrons?
You just do it.
Okay, but like, how does that work?
That's a really good question. You don't just really, we're balancing on paper.
Okay.
We're not balancing in an actual, like, jar.
Okay.
You'll see that what we're going to do is we're going to make these cancel. Because you
Alright.
can't just add electrons out of nowhere.
That's what I was saying.
Yes.
Just need a few electrons and you're good.
Yeah.
Because Mn has 2 plus charge.
So then why is
Got a
H2O
pile of
not?
electrons.
H2O doesn't have a charge? H2O is neutral?
Okay.
Did that answer the question?
Why are you adding 5 electrons?
To get this side to equal 2 plus? Because 7 plus 5 minus equals 2 plus.
Oh.
Wow.
Okay. God.
Math. It's okay. What's up?
The other side of the room is being very rude right now.
I know they are.
Why are they asking me?
I mean, she was really looking for, like, why are you adding this?
She's just confused, so she's thrashing out at everybody else.
Oh my god.
It's fine. Moving on. Okay, so is this reaction now balanced as far as charge is concerned?
Yes.
Yes. So my charges are equal.
Mm-hmm.
Are my atoms equal?
Yeah.
Please double check before you just say yes. Yes, we did things that do make sense, but check that you have 8 hydrogens on the left, 8 hydrogens on the right. Check that you have the 4 oxygens on the left,
Everything's ready.
4 oxygens on the right, and check that you have the 1 manganese and the 1 manganese. Yes, this one's right because I'm helping you do it, but when you are doing them, you want to make sure you haven't lost something.
And like the 5 is not relevant.
Correct.
Okay.
And you'll see why here in a second.
Then why
Our
do we do
goal,
it?
before we add them back together, is to make both reactions have the same number of electrons so that they cancel. And because this is a reduction-oxidation reaction, they will cancel. One of your reactions will have electrons on the reactant side, and one of your reactions will have electrons on the product side because of what we're doing. But let's go back to this one. This one's not balanced yet. This one is balanced as far as atoms are concerned. Is it balanced as far as charges are concerned?
No, man.
It is not. What is the charge on the left side of this reaction? -2. What is it over here right now?
+2.
0.
Oh, gosh darn it.
How do I get those two charges to equal each other? The only thing I can add at this point is something that doesn't have atoms, so it has to be electrons.
Yeah, you need 2
I'm going to add 2 electrons to the right side.
This is easy.
It's not bad. The basic ones get a little rough.
Oh,
Fair warning.
I
But
was just being sarcastic.
if you can follow steps, you'll be fine.
All right,
You have to practice by following steps, but you'll be fine.
that's it.
All right, so here is my one reaction. We are done with step 3 at this point because we balanced both according to charge and atoms. Our next step is going to be to try to get them to add together, but before we do so, step 4 says multiply each of your reactions by whatever you need to multiply by to get your numbers of electrons to be equal in both. So in one reaction I have 5 electrons. In the other reaction I have 2 electrons. What should I multiply this and this by, or what number of electrons do we want to go for?
10.
You can probably see it should be 10. If I multiply this one by 2, my number of electrons will be 10. If I multiply this one by 5, my number of electrons will be 10. Okay, so we're going to do that next. And this is before we add them together. Get your numbers of electrons to equal. It will save you a headache.
I already have one. Ugh, not mine.
Would I have 8 plus 5? Okay. What's up? Because I want the numbers of electrons in both half reactions to be the same.
So the number.
So you'll see if I multiply this one times 2, and then I'm going to take my C2O4.
Okay.
I forgot that this was the same one.
It is the same problem. So I'm going to take this whole one, I'm going to multiply it by 5, and I'm going to get so that's where I'm at. All right, next step is to do what? So this was step 4. Step 5 is to put them all together. That means add the 2 reactions to each other. So everything that's on the left is going to stay on the left of both of my reactions as reactants. Everything that's on the right is going to stay as the products in both of my reactions. So I'm going to add them together. All right? What's our next step? Cancel anything that's present on both sides if you can, right? What can I cancel? The electrons. That is the one thing you should always be able to cancel when you balance half reactions. Is there anything else I could cancel in this one? Doesn't look like it. So my final balanced redox reaction, that was the goal, is going to be in acidic solution.
Easy.
Oh, I never said it was easy. Sure. Jeez. Those are really dead.
Is it usually like smaller?
Not really.
We didn't even have to balance that side, like, with the atoms.
Basic ones can be smaller.
Oh, can you just move for a little second?
No, I said yeah.
Oh, I heard no. I was like, oh.
This is where we were. When we subtract our electrons from the equation, we get whatever's left over. That's it. With the basic reaction, there is an additional step of adding hydroxide ions to balance charges. This one was acidic, yes.
Okay, I
This
have-
was a balanced reaction in an acidic solution.
Okay, so for step 5, the 2MnO4 has a negative charge.
Correct.
Okay, final balance redox reaction.
Oh, it's supposed to be a negative. I'm sorry.
Okay.
My bad. I looked at the oxalate and put the
Oh,
two
no,
instead of the
no,
one.
no, you're fine.
He just caught a mistake. He just caught one of my boo-boos.
So good. I see the problem.
Okay. There is our final answer. Looks like what we just got. All right. Next thing's going to be what to do if it's a basic solution. Few slightly different things. Instead of having H plus ions present, we have to balance out those with hydroxide ions. Because in basic solutions, we don't have a lot of hydrogen protons. We have OH instead. So what we have to do at some point after we add H plus is to neutralize it by adding OH to both sides of the reaction. So to give you an idea of what this is, and we will balance a couple of basic reactions as well tomorrow, what that means is that since I added 8 H pluses here, I'm going to add 8 OH minuses here, and I'm going to add 8 OH minuses here. What this also then does, and we just said, OH plus H makes what? Water. What that means is that this will make 8 water on the left. There's already 4 waters on the right, right? Because that was our first step, was to add waters to balance oxygens. So we would then reduce this, and this will become a 4H2O. So what a basic solution does is basically create water in order to create a negative charge on the other side. Again, we'll go through it. We're not going to do one during lecture, but we are going to do one tomorrow. Yes, ma'am.
So you would leave the OH, but you would just get rid of the H2 altogether.
On the right side, because you have 8 on the left.
Yeah.
Yeah.
But then
But you would
you'd
leave
still
the
have 8
OHs.
OH, or would you
Mhm.
have?
Nope, you'd still have 8 OH on the right. You would still have 8 OH on the right, because you just added them, right? You can't cancel that out.
Too much.
Once you converted the stuff on the left to water, you have water on the left and on the right.
Would that upset the charge though?
It does. The next thing you'd have to do is continue the charge balancing, right? Like we'd go back and we'd look at our electrons. So it's a step that gets inserted between the H plus addition and the electron addition. Does that make sense? One additional step for balancing basic equations. Again, we'll talk about that a little bit more tomorrow. Just kind of keep in mind that the basic solution has one extra step compared to an acidic solution. All right, so that being said, let's talk about how this is actually used in chemistry. Okay, so these are voltaic cells. Voltaic cells are just fancy batteries for the most part, right? It's a transfer of electrons from one medium to another. Our voltaic cells are going to allow electrons to transfer and then release energy. So not just movement of electrons, right? The goal is not just movement of electrons. The goal is actually to do some kind of an energy release or energy transfer, energy conversion, you name it. Right? A battery, if you just put it on a bench for a really long time, will it eventually not work anymore? Yes. But if you put it in something, it'll lose its charge faster, right? It's a chemical reaction just like any other. Eventually it's going to run out of material to do its reaction on. When it's not being used, that reaction happens at a much slower rate. When it is being used, it happens very quickly. Most batteries have some kind of a purpose, whether that means to power your phone, power your computer, so on and so forth. That is an energy release of some kind. Okay? The beautiful part about the batteries we use in our day-to-day society is that we have come up with ones that are allowed to be recharged. That being said, are any batteries infinitely going to last?
No.
Not really that we have created quite yet. Quite yet. There's some promising research in nuclear waste batteries. Again, not an infinite battery, but a lot longer than a day. That being said, we're going to use that energy to actually get work to happen. Work can be in the form of producing light. Work can be in the form of moving something. Work can be in the form of allowing you to do something else, right? Performing some kind of a mechanical task is a really common work version. Think about the lawnmower example. If you're not really sure what that means, most lawnmowers are powered on either batteries or gas. If it's a battery, it's the same idea as gas. It takes that chemical energy and converts it into mechanical energy, right? The work that is being produced here is all from the conversion of energy from one form to another, and batteries are just a fancy way to do it. Reason batteries are so useful is because it takes a longer time. When we set this up, one of the things we have to do is we have to create a circuit. Okay, that means that two things are completely connected through various means. In a voltaic cell, there is something called a salt bridge that allows for slow distribution of ions. And there is also some wiring that is involved, right? You can see one here. There's electrodes, and they are usually placed in solution. The solution they are typically placed in is the one that allows them to be oxidized or reduced, okay? When voltaic cells are set up, they're going to have a few standard parts. The oxidation reaction, so we're still talking electrochem, we're still talking redox reactions. The oxidation part of the reaction is going to happen at what we call an anode. The reduction reaction is going to happen at what we call the cathode. And again, there has to be something that actually allows for a path to occur. Okay? So you can see that there are two different places where something can move along a path. Electrons are going to follow the path of least resistance and get to where they need to get as quickly as they can. In the case of this particular cell that you see here, we have a zinc anode, which is the negative side of our battery, and we have a copper cathode, which is the positive side of our battery, so our electrons move from the negative side to the positive side. Basics about electrochemical cells, that's what we're looking at here. And this is section 3 in your chapter. One of the things that they could not do is move without an entire flow of ions and electrons. So the other thing that has to be able to move are the anions and cations within your solutions. So in other words, we have to have the ability for these things to move, and we use what we call a salt bridge to do it. It's called a salt bridge because it's usually got salt involved. Please remember the things we were just talking about. Positive charges are going to move towards the negative thing. Negative things are going to move towards the positive thing. Hopefully that makes sense in your brain. That salt bridge is what allows that to happen. The anions and cations involved in the reaction use the salt bridge to move from one solution to another. That's the big takeaway here. Complete flow in order for this cell to work. If there was no salt bridge, you would see nothing happens here. There would be no reaction. You need both parts. You need something that connects the two, copper wire of some kind, and you need the salt bridge. All right. In a cell like this, one of the ways that we measure electron flow is what we call a voltmeter. Good morning. That voltmeter just kind of gives us an idea of how many electrons are actually moving and how quickly they're moving. One of the ways to impact that amount of electron movement is to impact how strong the solutions are between the two salt bridges. Salt bridges don't have to necessarily be something that connects two beakers. They can be just a barrier in between a solution. All kinds of salt bridges exist. And I think that's all I have to say about voltaic cells today. Yeah. All right, what questions do we have? Any questions? No? All right, tomorrow in class we're going to be working on balancing solutions. We're going to be talking about voltaic cells a little bit further. Your only homework is to finish up your lab if you haven't already.
Huh? Nothing, I was making another joke. Oh, I haven't eaten confidence.
That made me feel sick too much.
I don't think it really is.
Nice of you to show up this morning.